Today I will briefly mention kind of an introduction to the power of X topic and a few words about the raw materials typically used in these processes. Then the same applies to electrolysis of water. So it's the primary source for hydrogen, which is quite a key ingredient in these power to X applications. The second key ingredient, not in all, but quite many, is CO2, carbon dioxide. And basically that is the source for carbon. And if you combine hydrogen and carbon, so you end up with hydrocarbons, so which are organic molecules, and there are like millions of different combinations that you can make out from these two simple building blocks or elements, hydrogen and carbon. If you add there a few other elements like oxygen, nitrogen, some halides like chlorine, you already cover a lot of different important, industrially important products. Also a few words about something related to the challenges and future potential. Like I mentioned, so these slides are very simple. My idea is not to present every single detail. This is just to highlight some points. And we come back to all of these topics still in the coming lectures. So this is just not the end of the story, but just the very beginning at the moment. And I'm going to give you a lot of, let's say a lot, not a lot, but some research and review articles. And majority of this info that I present today and also in the coming classes, so it's based on the research articles or review articles that I use as the source or reference material. This you have seen already, and personally I like this graph because it kind of condenses the idea of power to X processes and many things within. So basically your task was, or your first assignment that I gave last week, so it was based on this article that I took this picture. So I called it article number 1. I number the coming articles like in the same fashion. So today you'll get articles 2 and 3, and later on I haven't yet decided how many are going to be part of this course, but in any case, so that's how the numbering and naming of this works out. So there are like power in the first of all, this name, so it has several variations. So you will find these power to X, or then some acronyms like P to X or P2X. These are very commonly used, but also in this course and in certain articles, so it can be that the X factor is defined somehow. Like I have organized the course so that the X is gas, liquid, or chemicals. So it can be also power to gas, power to liquid, power to chemicals. And there are several other variations to this, but it all refers to these very similar processes and approach, which in this graph is illustrated. There are key elements. The power, of course, could be whatever, but it's understood or it's referred to renewable power and renewable electricity. So at least not very often renewable heat, but it's more like electricity from wind turbines and photovoltaic cells. Then the other ingredient is that we consider starting materials, this very abundant and simple molecules that are plentiful in the nature available. So examples are here like water. It can be pure water or somehow unpurified water, but the main ingredient is this H2O water molecule that is broken to the elements or hydrogen and oxygen. And here the idea with these simple molecules actually is also the other simple molecule is carbon dioxide, and it can be obtained from different sources, different carbon dioxide capture methods. And what combines these chemically, these carbon dioxide and water, is that these are kind of, I have a chemistry background, chemical industry background, so these are actually some end products from spontaneous reactions. So if you burn hydrocarbons, you release energy, and then one end product is carbon dioxide. The other is actually typically water. And these are very strong molecules. These are quite difficult to break. You cannot easily get them reacting with anything because these are quite low in energy already. Usually molecules that have higher energy levels are more, let's say, have more tendency to react in a spontaneous way. But the spontaneous factor is not problem, or it's not in power to X applications, because we can go around and we can use forced reactions with the help of renewable power. So basically, the starting reactions, most of them are based on electrolysis technology. So basically, it means that you have to put energy into the system so that something happens. Because the other more common way is that if you think about a fuel cell, so you put fuel in and it produces energy. So this works the other way around, so that you basically put energy into the electrolysis cell and get these molecules to break into some products. Here are like some examples of this process. So primary conversion. Yeah, sorry.
Okay. For a second, I thought that you are presenting another slide, but we are still at the same slide, right?
Yeah, it's this chart that illustrates this. Or article number 1 should be written on the whole.
Yes.
Yeah,
It
there.
works. Sorry, my bad.
Yeah, no problem. Yeah. So this there are the primary conversion, which more or less usually is electrolysis based, and then there are these secondary conversions, like here in the lowest row of the chart, which says Haber-Bosch, methanation, and Fischer-Tropsch, and these are basically the very important chemical industry processes, very established, very mature technologies that are used today in the, let's say, petrochemical industry to make products. So basically the primary conversion is just generating the raw materials, and these raw materials can be further processed in the secondary, third, etc. following conversion steps. These are just examples of very typical, very basic bulk chemicals that are important, produced in huge amounts nowadays. Also, here are these P2X benefits. So if we compare with oil refinery and petrochemical industry, so those are these massive units, very centralized production. So P2X might offer benefits in this kind of smaller scale, numbered of decentralized production units. Also, one very important factor is that the renewable energy, like if we talk about solar or wind energy, it tends to fluctuate. No sun in the nighttime, no electricity. When it's a sunny day, no wind, so there is no electricity and so on. So this system, the primary function is in principle that it can store, in case you have excess renewable energy and there is no, let's say, need for that. So you can use the electrolysis technique to store it into chemicals like hydrogen, and which then can be later on used for something useful. So it helps in the seasonal energy storage problem. Also, of course, it can, in principle, as long as we use carbon dioxide, so it can at least diminish the use of fossil carbon or oil-based raw materials. These I took from some online source. The link is provided down below, but it's like putting this just the graph looks, or the table looks nice. There is basically the same elements that I already mentioned. So there is the renewable power, which of course provides the electricity for this processing step or the primary conversion. Then there is the different types of raw materials, like the water coming from, it can be pure water or anything, whatever. Of course, the process and the purification and things vary depending on the type of the raw materials, purity, and so on. Also, carbon dioxide is important starting material. You can get it from several different sources, and well, there are a few slides later on about this carbon dioxide sources. So basically, and here are some the product, what you can obtain from this type of approach. So you can store very simple molecules like, let's say, methane or hydrogen. It's a fuel. It can be used later on for producing energy. So it's kind of energy storage, but of course you can use it as a raw material to make, let's say, transportation fuels or more complicated chemicals that the chemical industry produces. So it offers an alternative way of utilizing excess renewable energy, making useful building blocks for this modern life that we are living at the moment. Very heavily chemical-based, fuel-based. Nowadays, majority of these are produced from crude oil-based materials and processes that process crude oil in the very beginning. And here is basically, again, this introduction, few sustainable feedstocks that are mentioned. We already talked about this, but kind of the renewable energy, seawater, wastewater, carbon source. So if you want hydrocarbons, so you need to have carbon at some source. So carbon comes from this CO2, different CO2 sources. So hydrogen comes from water typically. Then if we want to say ammonia, so there is nitrogen. So it's NH3, the formula. So you need to get nitrogen, but of course that's one possibility to extract it from air, which is the main component in the air here. So there's plentiful of that also. And the same applies to nitrogen as to CO2, as to water, that it's very stable molecule. Difficult to get it reacting in this molecular form that is found in the gaseous atmosphere. Here's a list of typical conversion processes. So basically just electrolysis of water making hydrogen, then converting it to CO, so carbon monoxide. That is quite reactive molecule. It's an ingredient in so-called syngas or synthesis gas, which typically is mixture of, let's say, carbon monoxide, hydrogen, and to some extent, smaller amounts of other gases. Then you can convert these into different chemicals. Methanol, for example, is quite useful chemical and also starting material for several different products. We'll take a look at these processes during the course. And ammonia is also very old industrial process, more or less 100 years ago, developed by this Haber and Bosch German scientists who got Nobel Prize for their original inventions. And why it's considered so important is that if we talk about food production, so food needs fertilizers to grow big crops and grow faster and better. So ammonia is the starting material for making nitrogen-based fertilizers, and that is the Haber-Bosch method is the industrial scale important method or first step in making these fertilizers. Here on the right-hand side, you see these different products listed again, but some of them are like, let's say, like here, these fuels. So this can be used as such, but many of them can be used as, let's say, feedstock or raw material for secondary conversions to other important materials. I think here is nothing that new anymore. I more or less explained this in that previous slide already. The same applies to these processes. We come back to these processes in more detail in the coming classes, but this can be typically classified as production of gas, liquid, and chemicals. Of course, these are very general terms, but usually when we talk about power to gas, we refer to methane or hydrogen at first and then methane. So these are the most common gases that are made, at least in these articles, and P2 gas approaches. For liquids, one can say that, for example, here I mentioned the simplest alcohol. Methanol is one that is produced in this power to liquids concept, but it can also refer to this utilization of Fischer-Tropsch process for making of hydrocarbons, so liquid hydrocarbons that can be used as let's say diesel gasoline replacement in mobile applications, aviation, and such heavy truck traffic transport. And these chemicals, power to chemicals, it's the most broad definition, at least in my view, because it contains all gases, liquids, and so on within the definition. But often there are something like ammonia, hydrogen peroxide, some more complicated formates, other chemicals that usually are connected to this power to chemicals concept or yeah. This has been taken from one of the articles that you get today. It's just a very simple representation of power to gas process. And this is methane production. So starting from electricity, electrolyzing water, producing hydrogen, then the other line you capture and condense carbon dioxide, and once mix hydrogen and CO2 in the reactor with suitable catalyst and suitable conditions, so you can carry out methane synthesis. And of course, this can be used for various applications. Currently, maybe not so much for mobility, but methane can be used in gas-powered vehicles and ships and so on. Also, one can use it for heating and generation of electricity. Gas to liquid, here's the similar scheme. In principle, basically you apply renewable energy to electrolysis of hydrogen, and also you mix carbon dioxide. There are several alternatives what could happen in this stage. But basically, you can come out with different types of hydrocarbons or organic molecules, and depending what is the application, you may upgrade them by treating differently. So this can be a multi-step process here, from hydrocarbons to upgrading to gasoline, diesel, jet fuel products. The other route here is making methanol, the simple alcohol, upgrading that, and also those products could be used in gasoline and diesel and jet fuel. And keep in mind, we dealt this already in previous courses, but gasoline, diesel, and jet fuel, these are very complex mixtures. So there are tens or hundreds of different hydrocarbons and molecules in that mixture. So those are not like pure chemicals, like let's say methanol or ethanol is a pure chemical, but gasoline is a mixture of several organic molecules. So just to clarify this a bit. And this also power to liquid, this could refer to power to chemicals. So one could understand methanol as a chemical, or certain hydrocarbons could be referred as power to chemical process products. So the approach is very similar. Usually there is in the beginning the electrolysis, then some chemical transformations which require certain reactors, catalysts, and so on. And of course, in between each of these unit operations, there is typical like separation or purification steps and so on. So this is very, very simplified scheme of the process itself, the actual processes. Products I already mentioned multiple times, but maybe here one thing that comes to my mind is that majority of these products that are made, so these are currently made from natural gas or crude oil and processed in traditional oil refining and petrochemical industry. And this power to X process or approach offers an alternative that in principle could use something else than fossil-based raw materials. And these are those that we discussed already. So water or green hydrogen from electrolysis of water, and captured carbon dioxide from different sources. So basically, although the production volumes are still marginal, this is new technology just gradually entering the market, but it's an alternative way of making those similar commodity chemicals important fuels that we use huge amounts of today, all produced from fossil-based raw materials. Okay, here's a few sources of hydrogen. Hydrogen is a very important basic chemical, already highlighted it multiple times. In principle, it can be produced from renewable, using different energy sources or natural gas, oil, coal, fossil-based energy. And depending on the process you apply, so there are multiple options: electrolysis, steam reforming, pyrolysis, at least mentioned in this slide. So hydrogen can be made in various ways. Some are more expensive, some are cheaper, and there are differences in these approaches. Also, when it comes to the source of energy, source of the raw material. This comes from the article number 2. We come back later on to these electrolyzer technologies, but I'm not sure if you have covered fuel cells in some of the previous courses, but these are in principle, very closely linked to the different types of fuel cells currently available. So there is close linkage to those. Fuel cell is basically running the same chemical reaction into spontaneous way, and this is running it into the non-spontaneous way, the electrolysis approach. Yes, so electrolysis, so it's the first step for breaking something. Lysis refers to breaking an electron with the help of electricity. So there comes the name electrolysis. If it's called, let's say, hydrolysis, hydro refers also to water. So in organic chemistry, for example, there are several hydrolysis reactions. So hydrolysis refers breaking with water something. This is breaking with electricity, and you end up with hydrogen, which is used, and of course there is the other gas, oxygen, as well, that can be used in certain cases. The table number 1 you'll see here, so it introduces 3 different electrolyzers, so also electrolytes and some operating conditions that you can find here, advantages, disadvantages, and so on. Then few words about carbon dioxide. So of course here is the nice idea, if you think CO2, greenhouse gas emissions, global warming. So there has been a big hype around this global warming and cutting of CO2 emissions, and this Power to X offers one, let's say, viable alternative for if you capture CO2 from different sources. So this is one potential process that could utilize the carbon. So in this sense, it's quite interesting. And here are listed some different carbon dioxide sources. Big volumes basically come from these industrial processes that we are running today. So let's say power generation, if you burn coal, if you burn hydrocarbons, fuel, if you burn oil, natural gas, so you end up generating carbon dioxide. It's a stoichiometric reaction, so where this hydrocarbon or coal combines with oxygen in the air, producing CO2 or carbon dioxide. That's something that you cannot avoid if you want that reaction to proceed. And if you have hydrogen there, so hydrogen burns into water eventually. Hydrocarbons produce CO2 and mixtures of CO2 and water. There's complete combustion of those materials. Petrochemical industry also produces. In the petrochemical industry is not part of the course. It's a very complicated multi-step industrial branch, and there are various products and processes, but in many of those processes there's release or production of carbon dioxide. And in principle, in certain parts it's cheaper and certain parts expensive, but it could be extracted, taken into use, utilized in the power to X applications as a raw material. Then several other industrial processes emit or produce carbon dioxide, like steel making, iron and steel processing, cement industry, just a few examples here. And well, on the right-hand side, there is also the biomass-based CO emissions or CO source. So of course, when I talk, I breathe, I inhale oxygen and exhale CO2. The same happens in whole living environment, and basically the same if you burn bioenergy, wood or something like that, so it combines with oxygen and produces CO2 as well. And in some facilities it's easier to collect or capture, and one is fermentation. So when we make, let's say, alcoholic beverages, or so there is release of CO2 gas, and it's quite easily captured in these processes. Much of it is used in alimentary industry to make these bubbly soft drinks and so on, but at least it's fairly simple to collect since the concentration is very, very high. Okay, what's the time? I have here, these slides are not that, there's quite a lot of text, but I copied this from, here is the original article, which is much nicer. You can have a look at it then if you want, but there are like in all, when you develop technology, so at the early stage, so there are a lot of, let's say, challenges and unknown factors in the implementation of these technologies. So this is kind of a list of some of these aspects related to power to X, and site selection is here first. These are not, I think, in my opinion, in any priority list. It's just a list, and and this site selection to find a suitable location that, let's say, we think so there should be access to the renewable energy source. So that's one, and also this, like let's say, central location, so that the end users or those who are using the products are nearby. So if we produce gaseous hydrogen as a product, so that is not the most easiest material to, let's say, transport long distances. Then second challenge might be to select the best technologies among the current available ones. So most of these technologies are being developed and improved, and when we talk about already mature old technologies. So there is a long history of these improvements and fine-tuning, and these have been optimized in all sorts of angles. But now when we talk about this quite new Power-to-X applications, so there are big problems in the beginning, and it's not yet there where we are fine-tuning selectivities, energy material efficiencies, and various things. It can be that some of them are the technology level can be quite rough still at this point, at this very beginning. And it's always when you set up a new factory, facility, production unit, so these economics are there. So the initial investment, it's usually high. Many of these chemical processes are designed for decades. So an oil refinery can run 50 years with some modifications, but in any case, so it's in the initial investment is big. And many of these challenges are general for if you are starting a new chemical process or new chemical production facility. Energy efficiency, of course, is important. So we utilize renewable energy, and how efficiently it's used, it of course reflects directly to the how much product you can get and what is the cost for the production. And then we come to storage and transportation. I already mentioned that in the previous slide. But here, if we primarily produce hydrogen, that's a gaseous chemical or molecule in more or less any temperature at this earthly conditions. So it's quite difficult to store, and when you mix it with more or less any concentration of oxygen, it becomes flammable and explosive. So there are safety issues and also capacity issues. So how to transport it. So like mentioned, so there is some specialized infrastructure needed, and also several safety aspects that are not necessarily that trivial ones to solve. I remember when I entered academic career somewhere at the end of 1990s. So quite soon there was this hype for fuel cells and for hydrogen-powered vehicles. And at that point, I think it ended. There is not that much talk about anymore hydrogen-powered vehicles and these fuel cell applications. But at that time, it was a huge problem with safety in mobile applications. The other one was how to store the hydrogen, because you have to compress it in very high pressure to get like meaningful amounts of hydrogen fueled in the car. So there can be that some of these problems emerge that are not yet solved and basically ruin the whole big nice idea or the chemical process. So one should not maybe take lightly, for example, the storage and transportation. If you cannot transport it where it's needed, so it's not very promising for that particular entering new technology. Market uncertainty is always an issue when you try to enter the market with totally new product, totally new process, and so on. So there are various question marks like here. So uncertainties regarding, let's say, pricing, regulations, demand, also like, well, many things that are not known because there is not a long history behind, not much about knowledge of these important details. And this has the regulatory and policy framework. This has been discussed a lot. It's not only about Power-to-X projects, but basically, let's say if you invest in this type of totally new chemical processes, ways of utilizing certain things, so it's a very time-consuming transformation before it becomes this commercial technology available to majority of the users. So this kind of evolution can take easily 20 years, 50 years. And industry is very allergic to regulatory changes or some kind of policy changes. So this regulations and policy that is not yet developed, so it's always a risk. So if there comes something that doesn't support the process or generates a lot of problems, so that's what is meant that the regulation and policy should aim for long-term guidelines, and it should not change in very short time period. And finally is the financing aspect here. It's linked to many of these challenges already mentioned in a way that you need financing, and with new technologies, it's not that straightforward and self-evident that you get financing, although you have the best idea, best technology, and so on. Also, there is the competition aspect. Maybe, let's say, maybe the current oil refinery industry, oil-based industry, doesn't want this new competing technology to enter the market. Maybe they, on purpose, try to prevent this technology from becoming the new next dominating major technology. I'm just guessing here of different possibilities. But the last thing here is that if we want this Power-to-X to be the major dominating technology, let's say after 20 years, 30 years time, so there's a lot of effort needed and collaboration of different stakeholders, industry, governments. Also, there is still lots to research and work for engineers and so on. So that was about the challenges, and then few words about the future. I don't have very many slides, so I think I will not have a break here in between, so I just continue. So if you have been listening what I was telling now for more or less 1 hour or 50 minutes already, so the future potential is of course culminating in somewhat this decarbonization. So some of these technologies that, or these products that Power-to-X processes make, so can help to get rid of this carbon in the fuels. For example, we can use, instead of hydrocarbons, we could use pure hydrogen, or let's say ammonia, and since it doesn't have any carbon atoms, so we, in this combustion process, we will not also produce any CO2, carbon dioxide. So it can help to, let's say, fight the CO2 problem that is man-made and the oil industry based problem. That is The second, I think it's in my opinion, it's quite maybe the most important one when we talk about power to X applications is that up to now, so the renewable energies, when we talk about renewable electricity, photovoltaic cells, wind turbines, so the energy supply is not continuous, and you cannot adjust it easily to match the demand. So this could help a bit by acting as an energy storage. So once we have excess energy, we can convert the electricity into hydrogen with these electrolysis processes, say. And hydrogen can be stored. If we are not happy storing hydrogen, we can of course implement it together with producing hydrocarbons or methane or some other more easily storable chemical. And once we need that energy, so this hydrogen or methane or hydrocarbons can be used for production of energy. So this energy storage aspect is quite, I think, key in this. There is really a need for storing renewable energy, and there are not so many applications available for making this. Of course, there are some ways to do it, but for example, battery technologies are not very viable still. And well, I will not go into this energy storage more, but in my opinion, it's very important in terms of the future potential. Then are these secondary things like environmental protection. That's of course very important to prevent global warming, reduce greenhouse gas emissions, and so on. But these are just problems generated by excess massive use of fossil-based fuels. But in principle, this power to X technologies can also reduce the use of fossil fuels and thereby help to protect the environment. And the last one, in my opinion, or how I understand, is that it enables use of renewable energy. And this is basically, there are certain sectors here, the so-called hard to electrify sectors, where these electric vehicles, batteries are not the viable solution. And this is like heavy industry and let's say this aviation and long-haul transportation. So if we transport goods and stuff with trucks throughout Europe, so there the electrical vehicles are not the working solution. If we talk about aviation industry, so there are some very first steps to utilize electricity in airplanes, but I think it's 99.999% still purely fossil-based kerosene that runs the airplanes. And basically these e-fuels or power to X-based fuels could produce from renewable sources totally the same fuels that the aeroplanes or the heavy trucks or let's say ships are using at the moment. So that's the key, that we could make those same fuels from renewable sources using excess carbon dioxide already captured or emitted in the air, and also utilizing water, which is plentiful to make these fuels. So there are a lot of good things about although there are these challenges that we covered a while ago. These are my old slides from previous courses. I think I had something to say about the big picture. So still the world is run by fossil-based fuels. And just keep in mind, this could offer a change to this, or at least some kind of change in the development, so that maybe the use of fossil-based materials would start to decrease after 20 years, after 40 years, who knows? But like the big volumes are in the crude oil, natural gas, coal-driven industries. Here is just where in different sectors where the fossil-based materials are used. And one of the biggest ones is the mobility applications. And here, let's say the power to liquids processes could help to produce liquid hydrocarbons that could be used in mobility transport applications. Also, oil industry currently is, or crude oil is the very important source for carbon, for hydrogen, for sulfur, for nitrogen, for many atoms and molecules that are used in making these everyday chemicals, products, whatever we have in the modern world. So this power to X could help to compensate so that some of the carbon, some of the hydrogen could come from renewable sources instead. Here is a very crude and simplified table, what is made out from oil, so what products. But let's say in this left-hand side, so power to X could offer a lot for producing, let's say, carbon products that we convert into plastics. There are a lot of solvents that are made from oil. Some of them could be made from these power to X processes. I will skip sulfuric acid. That is not relevant. One cannot make it. But then when it comes to these other organic molecules, so it might be possible. So you can replace the oil part with renewable alternatives, but still keep on living this crazy modern way of spending and using lots of chemicals and things we have today. The same applies here in the right-hand side, where there is the mobility and transportation. So power to X could basically produce more or less all of these are hydrocarbons, so it could be used to make these. So there's a lot of potential. But of course, the question one could ask that why it's not used yet. And there are several answers to that. First of all, it's quite new technology. We are at the very beginning. The other thing is always the money. So crude oil refinery, petroleum industry is so mature, so optimized, decades being developed. So it's very hard to compete with cost-wise. So typically these same products made out from crude oil, natural gas are much cheaper. But of course, situation can change due to various reasons. But that's one big thing, that would you pay like 10 euros for gasoline per liter now that the price is less than 2 euros? So very few would. But these power to X production processes at the moment are expensiver than their fossil-based counterparts. But